Okay, so first, we're going to do quizzes, the first quizzes next week. So in this class, quiz 1 is going to be next Friday. The quizzes are always going to be at the end of class, the last 10 minutes or so of class. And remember that to get ready for the quizzes, just reread through your notes, starting back at the beginning. Anybody have any homework questions that you'd like me to go over? Okay. I need to talk for a minute about temperature. Um, Temperature is different than every other unit that you're used to. And the reason that it's different is that the zeros of the different temperature scales are in different places. So, because hold on, 0 doesn't mean the same thing in the different temperature units. There's only 4 types of temperatures that'll come up ever in this class. Pretty much just 2, really. So Celsius, Fahrenheit, Kelvin, and Rankine. And excuse me, the Kelvin and Rankine scales both have their zeros at absolute 0 temperature. So that's when all molecular motion stops. Other than that, Rankine has the same, like a change in temperature of 1 degree Rankine is the same as Fahrenheit, and a change in temperature of 1 degree Kelvin is the same as Celsius. So these two are connected, and these two are connected. Because the zeros are at different places, or at different temperatures, conversions of instantaneous temperatures are different from conversions of changes in temperature. So that's not true with, measurements of length, or like if you're talking about this single object is 1 meter long and you want to convert that to feet, That's the exact same conversion as saying this object has changed its length 1 meter. Convert that to feet. You do that conversion the same way. But with temperatures, you can't because of the different zero meanings. So for instantaneous temperature conversions, the temperature in degrees Fahrenheit is the temperature in degrees Rankine minus 459.67. So absolute zero is at negative 459.67 degrees Fahrenheit. The conversion between Fahrenheit and Celsius, the temperature in Fahrenheit is 9/5 of the temperature in Celsius plus 32. And the conversion between Celsius and Kelvin, the temperature in Celsius is the temperature in Kelvin minus 273.15. I'm almost always going to leave that 0.15 off. But so absolute zero is at minus 273.15 degrees Celsius. Yep.
Professor, for the first equation, what is degrees are?
That's the Rankine scale. You don't see that used very much, but the same way that Kelvin is Celsius degrees, but zero is at absolute zero. Rankine is Fahrenheit temperature, but with zero at absolute zero. We won't. I don't know if we use it a single time in this class, but if you hear it, that's what it means. Okay, but what about changes in temperature? So a change in the Fahrenheit change in temperature using Fahrenheit units is the same as the change in temperature using Rankine units. A change in temperature using Fahrenheit is 9/5 of the change in temperature using Celsius. And a change in temperature in Celsius is the same thing as a change in temperature using Kelvin. Okay, so if you don't keep track of whether you're talking about a change or whether you're talking about an actual given temperature that's occurring, then your answers aren't going to make any sense. Like think about a case where the gas, the system that you're looking at, increases its temperature by 5 degrees Kelvin. What's the change in temperature in Celsius? Well, if you do it the right way, you can see that it's also plus 5 degrees Celsius. If you do it the wrong way and use the conversion that you would use for an instantaneous temperature, you get that the Kelvin temperature goes up 5 degrees, the Celsius temperature goes down 268 degrees. That doesn't make any sense, you know. Okay, so just a quick example. So first, let's say the temperature is 305 Kelvin. What's the temperature in Celsius? We're almost always just going to use Kelvin and Celsius. And then second, the temperature decreases 15 degrees Kelvin. What's the change in Celsius temperature? So for the first one, is that an instantaneous temperature or change? Yep. So we're going to use the formulas here. And so we have that the Celsius temperature is equal to 305 minus 273. So that's 22. So 22 degrees Celsius.
22?
20, 30, 33. 273. So that's, 32. Thank you. For the second one, is that an instantaneous temperature or a change in temperature? That's a change. And so a change in Kelvin is the same as change in Celsius. And so the Celsius change it's a decrease, which means the change is negative in Kelvin. And so this is negative 15 in Celsius too. Yep.
Professor, when converting, should we use 273 or 273.1?
I think I always leave the 0.15 off. Either one is fine. Okay. Any questions about temperature? So now we're going to talk about, this is kind of the first topic in thermodynamics for us, the first law of thermodynamics. And this is conservation of energy. And remember that in physics 1, we had the conservation of mechanical energy. And it said something like this. Delta E is equal to the work of all the non-conservative forces, where this E was defined as the kinetic energy plus the potential energy. Um, okay, so T is the kinetic energy. V is the potential energy. Um, and the way this kind of works is, so really, I don't know, different classes talk different amounts about like the work energy principle and stuff. Do you remember the term the work energy principle? Probably as a lead in to conservation of mechanical energy. Um, so the work energy principle says that the change in kinetic energy is equal to all the work done. Okay. No matter what kind of force is doing work. So that's a nice simple form. But that's before you start thinking about potential energy at all. Anybody remember what is required of a force to be able to represent it as potential energy? This kind of stuff gets kind of glossed over as you go through all the problems and stuff, but potential energy only exists for conservative forces. Okay. And like the conservative forces that you dealt with were gravitational fields, um, and spring forces, and then maybe electric fields or magnetic fields. Okay. But remember what a, do you remember what a conservative force is? Anybody remember the definition of a conservative force? Okay, a conservative force is one where if you're given the location, that's enough to know what the force is. Okay, so gravity is an example of that. Like, even if you take the more complicated definition of gravity that depends on the distance, okay, if, if like this calculator, say we measure its mass, and then you tell me where it is, how far it is from the center of the earth, and I can tell you the force on it. Okay. And it doesn't matter how it got to that location or anything like that. The location is enough to know. That's different than most things. Like, let's say uh, what's the friction force on this thing at this location? Well, that we don't know that because if it gets to this location as I slide it this way, the friction force is going to be this direction. If it gets to this location sliding this way, friction force is going to be the other direction. So in both cases, it's at this location, but the force is different. So that's a non-conservative force. Okay. And basically and so if you have a conservative force, you can define its work in terms of a potential energy function. That's why we define potential energy. It's just an easy way to calculate work. And we use this definition that said the change in potential energy is the negative work. Okay. So all that is like for gravity, when you're calculating the change in potential energy as it goes from this location to this location, you're just using a simplified way to calculate the work that gravity does. Okay, so now this is what you did before, right? Uh, in thermodynamics, we're going to include thermal energy. Um, and so now we're going to define the energy as, of our system. We're going to define the energy of our system as the kinetic energy plus the potential energy plus one new thing, U. And so this is the kinetic energy. This is the potential energy. And potential energy only exists for conservative forces. And then U is called the internal energy. You can think of that as thermal energy. That's how much the molecules, how fast they're moving, uh, the temperature. It's related to the temperature. Um, and energy changes can happen through the work of non-conservative forces or through heat transfer. And I'm going to call that Q. Okay. So work, to make a distinction between work and heat, work is an energy change caused by the application of a force. And heat is energy change caused by a difference in temperatures. Okay, so we're starting with the same exact thing that we did in Physics 1. We're going to include two new little things. We have a thermal energy term in our energy, and we also have this new thermal way of changing energy. Okay. And then the last thing we have to deal with is the odd sign convention that I already, told you about before. But this is just something you absolutely have to get used to. So this key point is that you have to get used to an odd sign convention. And that is that Q is positive when heat adds energy to your system. And W is positive when work removes energy from your system or adds it to the surroundings. Um, and to remember This sign convention, think of a heat engine. You have a piston and a cylinder. Your gas is in here. That's your system. You do something to raise the temperature of the gas, and the result is that that piston rises. So you increase the temperature of the gas. That's positive heat into your system, and the result is that the system does work on the surroundings. Turns a crankshaft or something to get useful work out of it. It's how an internal combustion engine works or whatever. Okay. So, okay, with all that, the first law of thermodynamics says the change in energy is equal to heat added to the system minus work taken from the system. Okay? It that negative sign really kind of obscures the simplicity of what we're talking about here. Like all we're saying is the amount that the energy of your system increases is equal to the sum of the energy increase due to heat and the energy increase due to work. But since our W means actually energy leaving the system, we have to have that negative in there. Okay. And then the definition of E.
Professor?
Yeah.
So when work is done to the system, we put that in Q?
No, it's just negative then. So yeah, if you
negative minus negative W.
Right, exactly. Okay. Yeah, and that which comes out positive and adds energy to the system. So and this energy is the kinetic energy plus the potential energy plus the internal energy. So there is our, I don't know, probably our most important equation in this class. One thing that I didn't put in here, and I'm not going to put in here, it's not normally written this way, but remember that work only refers to the work done by non-conservative forces. So I'll write that in red, but that's non-conservative. And then that V, that potential energy only exists for conservative forces. Okay. And just like the work energy principle, we could have written this equation in the simple form delta E is equal to Q minus W, and then just not written the potential energy thing at all. That work would just have to represent the work done by conservative and non-conservative forces. Okay, that's how you did it in physics 1, too. What? Can you say that one more time? Yeah. So we are used to breaking up work into the work done by non-conservative forces. And then instead of thinking about the work done by conservative forces, we represent those in terms of potential energy. That's why this is only the work done by non-conservative forces, because we include the work done by conservative forces in this V. Okay? Another way to think of it would be to have no V there, and then this work just represents all the work done. But the reason we do it this way is because potential energy calculations are an easy way to calculate work done by conservative forces. Okay, so that's why we break it up that way. Um, okay, one thing I want you to notice. Unless there is a reason in the wording of the problem, so unless there's a reason to believe otherwise, otherwise, um, most of the time, we're going to have the change of kinetic energy um, and the change in potential energy. Just treat those like they're zero. Those are going to be small compared to the other stuff. Okay. Um, so in that case, uh, delta E is really just the change in internal energy. And we'll get into a lot of ways to calculate internal energy, figure out internal energy for different substances and stuff. Uh, what would be a reason to believe otherwise? Well, if it says something about your system going from this speed to this speed, then okay, then we're going to have to deal with the fact that the speed of this, I mean, like if your system is an object and it's flying through space and the speed is changing, then okay, the kinetic energy is changing. Or if it says something about your system changing heights, remember that's gravitational potential energy has to do with the height of the object. So if it says something about the height change, then okay, you got to put that in there. But if it doesn't mention stuff like that, we're just going to assume that the change in energy just has to do with internal energy related to temperature. Yep.
Professor, so like if you have a car and it crashes into a wall and the wall like doesn't move at all,
Yeah.
like would that all be heat? Or, like,
The so if you
kinetic goes to zero and it doesn't
like if
move.
your system, if you're analyzing the car, like where would all that energy go? Um, well, yeah, you could think of it as work. Uh, Even if it's a perfectly elastic collision, so even in a case where none of it goes to heat, like imagine a super ball hitting the wall, that energy, uh, like think of that as it does negative work on the object because the force is in the opposite direction as the velocity, so it slows it down, and then it speeds it up going the other direction. So, any other questions about this? This is all kind of just set up. I think it'll start to solidify more as you start to do calculations. But basically, you could you could have slept through everything I said up to this point. This is the stuff in the box is what we're going to use, and we're usually going to say delta E is just the change in internal energy. Um, the most common type of work in this class is the work of expansion. Um, And the work of your system expanding is the integral from the starting volume, to the ending volume. We're sort of running out of letters, so be careful here. Capital V means potential energy in this stuff above. It means volume here. And we're taking the integral of the pressure of in your system, dV. So V and dV here refer to volume, not potential energy. Um, One thing that this tells us uh, is that the work is always positive if the gas expands. Um, the work is zero if the volume stays constant. I mean, not the total work isn't necessarily, there could be other stuff going on, but this work of, I'm talking about the work of expansion. And the work is negative if the gas contracts. Okay, what would you need in order to compute this integral? Um, well, what you need is you need to know the pressure as a function of the volume. Uh, and what you're hoping for, it's even easier in the somewhat common case that the pressure stays constant. So this is just kind of advice. Keep this in mind. If you have a way to calculate the pressure as a function of volume, so if you can calculate P as a function of volume, or if the pressure is constant, look for ways to calculate the work of expansion. Okay. Um, like as these problems are put together, uh, if if the problem gives you a way to calculate pressure as a function of volume, or if the pressure is constant, often the reason that the problem is giving you that ability is so that you can calculate this work of expansion. Okay. All right. let's put all this together in an example. So let's say that the pressure is constant at 1.30 times 10 to the fifth pascals. And so this is the pressure in this gas, and the gas starts at 0.35 cubic meters. And then the piston, so this gas is like in a cylinder, and then the piston is pushed down. And the volume decreases to 0.2 cubic meters. So first, what's the work of expansion? And then second, if there's no work other than expansion, and the cylinder is well insulated. So saying that something is insulated means that there's no heat transfer. That's what you do when you put, drinks in a igloo cooler, is you're trying to make it so there's no heat transfer between what's outside the cooler and what's inside the cooler. What's the change in internal energy? Okay, well, you're given that pressure is constant, and that should ring a little alarm in your head that says, I can I can calculate the work of expansion. Is that useful in any way to me? Well, in this case, it's explicit in the problem that, yeah, that's the first thing you want, is to calculate the work of expansion. But to make this problem a little harder, all I would have to do is not ask you part A and just ask you part B. Okay? Then it's not immediately obvious that you have to calculate the work of expansion, but you do have to calculate it in order to do part B. And the way that you should see that that's maybe true is the fact that it gives you the constant pressure. Okay, so
Professor,
mhm.
I was wondering if you only had the part, like it didn't say that the pressure was constant, just said that the gas started and then the piston pushed it down and
Yeah.
compressed it. Would that mean both the heat and the pressure would increase of the gas inside?
We just don't know. I mean, we just don't have enough information to do it.
Okay.
Yeah.
So then we would need either a change in heat, so then we can find the change in pressure.
Yeah, right, exactly. We just have to be given more information in some way about the behavior of the gas, and yeah. Okay, so the pressure stays constant. So the work of expansion is the integral from the starting volume of 0.35. By the way, I'm keeping all my units in SI units, which is what I would recommend. Then you just know all this stuff works together and you don't have to think about carrying units through your calculations. It ends at a volume of 0.2. The pressure is 1.3 times 10 to the 5. And we're integrating with respect to volume. So you can pull, because the pressure is constant, you can pull it outside the integral. And you get 1.30 times 10 to the 5th times the difference, 0.2 minus 0.35. And you get a work of expansion of negative 19,500 joules. Okay, does it make sense that it's negative?
Yes.
Yes, the volume decreased, and I said here, it's always the case that if the system expands, your work of expansion is positive. If it contracts, your work of expansion is negative. So that's good. How much energy is this? Like, what do you have to compare? Well, think of like the amount of calories you eat in a day. Basically, like we deal with big amounts of thermal energy. This is very small compared to the amount of calories we eat in a day, which is about, I think it's about 8 million joules of energy.
There are 4.184 kilojoules in 1 calorie.
Yeah, right. And then for part B now, we're going to use the first law of thermodynamics. So it says the change in energy is equal to the heat added to the system minus the work done by the system onto the surroundings. If I expand the meaning of E, that says we have the change in kinetic energy plus the change in potential energy plus the change in internal energy is equal to Q, which, well, I'll cancel stuff later, minus W. And we just figured out that W is negative 19,500. So this is minus negative 19,500. We're not given anything about the change in speed or the change in height, so I'm going to ignore those like we will most of the time. It's insulated, so Q is 0. And so the change in internal energy is positive 19,500. This is in joules, SI units. And it's not always it's not always true. There are some counter examples that we'll talk about and stuff, but for the most part, you can think of like increasing internal energy is just increasing the temperature. So what we've done here by reducing the volume of this gas is increasing the temperature of the gas. How much the temperature increases depends on the type of gas.
If you decrease like the volume of the gas, wouldn't that also just make like the molecules move more rapidly?
Right. Yep. And that's what temperature is. Yep. Yes.
Professor, so like you said, like we can't if we're just given the change in volume, like we can't specifically find like
Right.
the change in pressure and the change in thermal. But you said like for materials, like if we're given that it's like nitrogen, then could we find it out? Or
Let's see. If you
with those
knew,
tables?
there are tricks you can use for different types of processes. So, and we'll sort of, that's the kind of thing that as the class goes on, we'll say like, okay, what if it's this kind of process? We could use that to simplify this. And you can sometimes get it sort of approximations that way. Yeah. Any other questions? Okay, so the quiz is not this Friday. It's a week from Friday. All right. See you later.
And they'll be